Welcome back to ECE 442-542. Homework number 6 is due today. We have a review session also today that will be after this class, and it will actually be in this same room. So we don't have to close up and reopen. We'll just stay here. Hopefully we won't get kicked out. I was told they don't have a class here tonight, so we'll stay. We'll try for staying here. I will get us through some of the material, but there's actually a little bit more material that I'm expecting I won't be able to get through today before exam number 3, and that's what I'm labeling lecture 6.4. It's not a 75-minute lecture, but it does go through one example that has 2 real poles and a 0 and this circular root locus. It's similar to what you may have on a homework problem, so you might want to look at that even after class and check your work or look at what you're doing on your homework. Exam number 3, I hope, comes as no surprise that that's the next time you come to class. Not for the review, but for the lecture. That's this coming Wednesday. So tell your classmates that there is an exam coming up on Wednesday. Today I want to simply tell you that you get one more sheet of notes. That's basically the process. It's the same as what it has been before, the process for number 3. And then we will start looking at just a very quick summary or review of the proportional controller, and that hopefully will lead us into the PI controller and how you can essentially address that by, again, adjusting this gain K. But then we will get into an example that shows or illustrates why you might want a PI controller versus a P controller, a proportional integral controller versus a proportional controller. And that will be after we've quickly breezed through the summary of 3 of the root locus rules, and if we have time, we'll get into the last 2, but you won't necessarily need those, I don't believe, for exam number 3. But it'll be nice to have them all in a package, but I don't know that we'll have that before we finish today's class. The process for exam number 3, again, you get one more sheet of notes. Oh, I didn't say a transform table, did I? A calculator, something to write with. You can actually bring a protractor and a straight edge if you want, if that helps you sketch quicker or more neatly. I'm all for neat. You wouldn't know it by the lectures, but then there's all the no's. The no cell phone, no computer, no textbook, no class notes, no classmate, no talking. Let's get into, and the topics are basically homeworks 5 and 6. That's what the material is for exam 3. We'll talk a little bit more about that at the review session tonight at 7. Now let's get us ready for exam number 3, and part of that will be sketching root loci based on having a P controller or a PI controller. The P controller, we just have a gain K that we're adjusting from 0 to infinity with non-negative values for K, and that leads to this closed loop transfer function, and we're really adjusting the closed loop dynamics by moving that control value K from 0 to infinity. And a lot of the times I might simply be asking, is there a range on K for stability? Is there a lower bound? Is there an upper bound? Is the lower bound 0, etc.? Or can you just go from 0 to infinity and it stays stable? You could do that in analog, but that's no longer usually the case in digital. It could be, but not very often is that the case, where you have all this freedom or flexibility in adjusting the gain parameter. This is the structure then. We have an isolated gain with some plant, g of z. Let's now look at the PI controller. And to get us thinking about what that looks like, if we examine the analog version or form of a PI controller, we're simply taking the present air signal, E of t, and scaling that with an adjustable parameter, k sub p, and we're taking the integral of the air signal and scaling that independent of the instantaneous air. K sub p and k sub I are independently adjustable in a PI controller. And if you bought a PI controller, which you can off the shelf, you have knobs that you can adjust or tweak. One of those knobs being Kp, one being Ki, or the proportional knob, the integral knob, and the derivative knob. And here we're setting the derivative knob, the PID, the D part, to 0. We're not introducing that. You can Laplace transform that time domain expression for a PI controller, and now we have this expression in terms of K's and S's, Kp, Ki, and S. We can actually do our discrete equivalent that we've done before using many different techniques. Let's just use the forward technique. That's about as easy as we can get, where we simply replace S with z minus 1 over t. The difference in these two time instances divided by the sample period. That's this approximation of S to get us from analog or continuous time into discrete. And now all we're going to do is perform some algebra to see what the generic structure of a PI controller looks like in the discrete setting. We have a z minus 1 in the denominator. That sample period t, let's put upstairs since it's in the denominator of the denominator. And we can factor out the transformed air signal, which is E of z, and now we have a proportional piece and an integral piece in a discrete time transformed control setting. We can obtain a common denominator between the two pieces so that now we have one denominator factor or polynomial, and now where is the root of the denominator located? That's not a tough question. We just set the denominator equal to 0 and evaluate it. That's z equal 1. We have a pole in our controller at 1. And that's similar to putting a pole at the origin in the S domain. Now our integrator in the discrete time gives us a pole at z equal 1. That's forcing a pole. We don't have any choice in that matter. We have a fixed pole at the z equal 1 location in the z-plane when we introduce a PI controller. Where we do obtain our flexibility is in the numerator, which if we simply start to factor that, we see that we have a term that involves the z, and we have a constant term. And if we pull out the gain on the z term and basically lump k sub p minus k sub I t over k sub p, that becomes alpha. This is now our generic structure for a PI controller in a discrete time setting. If somebody says, oh, introduce a PI controller, boom, you plop a pole right at z equal 1, you put a 0 somewhere, a real 0 somewhere, and that's probably going to be between minus 1 and 1. It wouldn't have to be, but generally it would be. And then you have this adjustable gain, k sub p. That's the way of thinking of a PI controller. looking at it slightly differently than just adjusting a case of P knob and a case of I knob. Now we can say, oh, we have a 0 to locate and we have the gain to adjust. That's how to think about a PI controller, because this class is a controls class. We're trying to figure out how do we use, for those of you that are listening, you can't see what I'm doing, but I'm flavoring my Z-plane with a 0 shaker and a pole shaker, and I'm sprinkling poles and zeros in the Z-plane to try to improve the dynamic behavior of the closed loop system. Just like you enhance the flavor of your food by seasoning it, your seasoning in a control setting are zeros and poles. With a PI controller, your pole shaker is fixed. You don't even have to move that. You just get a pole that plops right at Z equal 1. The 0 you can adjust, and then you tweak the gain, K. Questions on that PI structure that now you can play with in the Z domain or in the discrete time setting? What does that bias? Not B-I-A-S, but B-U-Y-S. What does that give us? It gives us a couple of things. One is it forces that pole at Z equal 1 in the open loop transfer function. In the product, in the cascade combination of the controller, C of Z, and the plant, G of Z, it forces an open loop pole at Z equal 1. That actually is what? It's right on the stability boundary. It's right on the unit circle, so it's probably not improving our transient behavior. We're buying steady state accuracy with that introduction of that pole at Z equal 1. We're trying to enhance the steady state accuracy of our system by introducing a PI controller, which really says that if you now have a PI controller and you can stabilize the closed loop system, you're guaranteed, no matter what you set your gain at, as long as you set it to make your closed loop system stable, your steady state error due to any constant will be 0 because of that pole at Z equal 1. And we'll try to work through an example that verifies that today. But a PI controller guarantees that constants, when you apply those to your system, have 0 error. You have perfect tracking of that constant. So if you turn your wheel to 10 degrees, you're going to go right to 10 with your system. If you say go to 3, whatever 3 represents, you're going to be locked right on 3 with a PI controller. Your transient, you'll have to adjust by the selection of the 0 and that gain. And you may be trading off some transient performance for steady state accuracy. That's this trade-off that you always have in a control setting, is steady state accuracy versus transient behavior. The second piece that becomes in play or comes into existence with a PI controller is this adjustable 0, that's the alpha, and that's influenced by K sub P and K sub I and the gain K bar. But if you just say, oh, I want a 0 here at some alpha, you can back out the gain values for K sub P and K sub I. And K sub P is really just that K bar. You have the ability to select alpha and K bar in a PI controller. But that block diagram is, I hope, trivially equivalent to just having an adjustable gain once you've fixed this 0 at a value of alpha. Now we've changed the block diagram very slightly, but now we have a G bar, and now we have it in the standard root locus configuration. I give you a G bar, you give me a root locus. Is that clear? I hand you a G bar, Exam number 3, you have to be able to produce the root locus for that. And the root locus just tells you where your closed loop poles belong for every possible value of k bar. That's what the root locus is. But I hand you a g bar, you give me a root locus. Is that clear? That's exam 3, part of exam 3, but I hope it's clear that if I give you a P controller or a PI controller, you can generate the root locus for either of those two scenarios. And eventually, you're going to learn how to select alpha based on your expertise in the root locus diagram. You'll start to become more comfortable with, oh, if I just put a 0 there, then my branches of the root locus would behave like I want them to. And I could now place my closed loop poles in the appropriate location to achieve the transient that I want. And if it's with a PI, you maybe already have the steady state accuracy that you were looking for. Again, that K bar allows you to manipulate the closed loop poles, but you don't have total freedom over those closed loop poles. Where are the closed loop poles? Where do they live? What's a one-phrase description of where do the closed loop poles live? On the, here's one answer that I would have to accept unless I gave you more information. On the z-plane. But you can be more specific than that, right? They're on the root locus. Where do you fix them on the root locus depends on your choice of k bar. You sketch the root locus and then you say, oh, I want my poles to be here on that root locus. Then you've determined what your k bar is, what your gain is to get you to that point. But where your closed loop poles or where your dynamics of the closed loop system are governed by the denominator of this closed loop transfer function. And those are determined by the root locus. Yes? It's off topic. Oh, good question. So the question, that's not so off topic. The question was, can I put a pole at z equal 1 if I already have a 0 at z equal 1 in my system, in the original g of z? Did I hear the question correctly? Then you probably don't want to do a PI controller, because then you have a pole, a closed loop pole, forced or fixed at z equal 1, and that's on the stability boundary. And if somebody gives you a constant, that's going to go unbounded with time. So you could give them a bounded input that will produce a bounded output. Now that unbounded output may not be theoretically in your system between R and Y. It might be somewhere hidden inside your system. And then you might, looks okay, but it smells a little hot. It might burn up on you. Okay? So yes, if your g of z happens to have a 0 at z equal 1, you probably want to avoid a PI controller. So a PI controller is not a cure-all, but a PID controller does allow you to control a lot of different systems. If you're not happy with the transient that you're getting with a PI, sometimes you can introduce the derivative term to enhance your transient to what you need, and so a PID controller may be sufficient. And that covers a lot of the control systems in the world, is the PID controller. So knowing that and being able to adjust that effectively is a good piece of knowledge to have. Just as a review, the root locus are those values of z that satisfy that equation, and the values of z that satisfy that equation are your closed loop poles. To establish some notation, now I'm simply saying that g bar of z is this ratio of polynomials, a little n over a little d. So no matter what you start with, I've combined your poles and zeros of your plant and controller into one polynomial numerator n and one polynomial denominator d, and that gives rise to, when you look at 1 plus k bar g bar, obtaining a common denominator in that expression gives you then a numerator. That's really what you're looking at, d of z plus k bar n of z. If you now set k bar equal to 0, what values of z satisfy that equation? The roots of d, which are your open loop poles. If you let k bar get really, really big, then what values of z will satisfy that? Well, k bar n of z is going to dominate that expression. Now your z values that satisfy that for large values of k bar are your finite zeros, the values, the roots of little n of z. And that's, I hope, somewhat clear from that numerator expression that governs the closed loop poles of your overall transfer function between r of z and y of z. You only have to listen to me for a little bit more, and then we will slow down and start playing with some examples. Here are some quick summaries of the first 3 rules of constructing the root locus. And rule 1 you could just think of as beginning and ending of the root locus. Where do you start your root locus? On your open loop poles, those values of z that satisfy d of z equal to 0. Where do you end your root locus branches? The finite branches terminate on your finite zeros, and then if you have infinite zeros, they're going off to infinity. Now, how many branches of the root locus do you have? The same as you have roots of d of z. So the order of d of z, if d of z is 6th order, you have 6 branches of the root locus. And 2 of those branches might be on the same line segment. So the number of line segments that you have is not necessarily related to the branches of the root locus. The numbers may not be the same. That's rule 1, where you start and where you finish. Rule 2 now tells you which pieces of your French bread belong to the root locus. And that's just this, you're looking for odd numbers of poles and zeros to the right of each of those segments. That's rule number 2, which are these, which real axis segments belong to the root locus. And rule number 3 concerns these breakaway and reentry points. If you have a breakaway, do you have a reentry? It depends, right? You wouldn't have to. If you have a reentry, do you have a breakaway? Based on the systems that we've looked at so far, you would be wanting to say yes, but you could have started with complex poles, and they may re-enter the real line without ever breaking away from the real line. A breakaway and reentry do not have to be paired up. You don't have to have one and the other. Yes? Rule number 2 is assuming that all of your poles are complex conjugates of each other. And you don't have to worry about the poles and zeros off the real axis to apply rule number 2. So you could be blind to what's happening with poles and zeros located off the real line as long as they are complex conjugates of one another. They come in pairs. Correct. If you have a complex pole that doesn't have a conjugate, you've probably lost some points because you now have coefficients that are complex somewhere in your expressions, and we're not going to play there. We're going to play nice. We're going to have polynomials with real coefficients. And so we will have pairs of poles and zeros that are complex conjugates. Does that answer your question? If you had a question, it was more of a statement, maybe initially. So we'll play with complex conjugates, and if you have poles and zeros that are off the real line, you really don't have to worry about those in identifying the segments of the real axis that belong to the root locus, because their angle contributions are going to always cancel each other on the real line because they are appearing in conjugate pairs. One will give you a positive angle, the other will give you just the negative of the same value. So you don't have to worry about off-axis poles and zeros. Other questions on our 3 rules? The other 2 rules are, just to fill you in, we will learn how to sketch asymptotes, which is where the root locus branches go as you really crank up the gain k. One you already are very comfortable with, which is the negative real line. That's one asymptote. That's at minus 180. Another characteristic asymptotes are the plus and minus 90. Those are asymptotes that you've seen. But pretty soon we'll see that we have asymptotes that split 360 degrees equally. So there's one at 60, one at 180, and one at 300. We could have 4 and how do we get asymptotes? Those are associated with our zeros at infinity. That's rule number 4. Rule number 5 is if we do have off-axis poles and zeros, it would be nice to know how does the root locus leave those poles, those complex poles, or how does it approach or arrive on finite complex zeros. That's rule number 5. We'll get there maybe before exam 3, but I'm not going to promise it. You don't need it, I don't believe, for exam number 3. That's not very comforting, is it? Reassuring. But know everything up to and including rule 3, and you're fine on exam 3. Let's now look at this comparison of proportional and PI control. And we're going to do it for about as trivial of a system as you can have. This is now a discrete time system. What is that system? If somebody gave this on an interview and they said, here's your system, G of Z, 1 over Z, what does that represent? It's simply a delay, isn't it? It's a 1 unit delay. It's a 1 sample period delay. That's all it is. So now we have a delay, and we want to introduce feedback and try to control that system, maybe to make it behave a little bit better for whatever reason. So now let's look at the range of K for closed loop stability. And now when I'm looking at this, probably when I start saying range of K for stability, that's sort of code talk for, oh, he's probably wanting a root locus, and I need to figure out where those branches are relative to the unit circle so that I can maybe find a minimum and a maximum to bound my gain k. If I wanted the closed loop transfer function, what would that be between r and y? Just to get us thinking in the same, on the same page. This is our cheer. That's just k, g of z over 1 plus k g of z. And if we look at the denominator of that, which is governing our closed loop poles, we have 1 plus kg equal to 0. But if we're looking for values of z that cause that to vanish, we probably want to look at the numerator. So let's put everything over a common denominator of z. And then we have z plus k equaling 0 in the numerator. Meaning our numerator of that expression, of that ratio, is what we're interested in. And now we want z plus k to equal 0. The strategy then is to go ahead and select k in order to keep the roots of that polynomial, which is first order, and it's just z plus k, inside the unit circle. That's one way of thinking of it. Or if you thought of it in terms of a root locus, then we have the 1 plus kg of z equal to 0, or kg of z equal to minus 1, which is 1 magnitude at an angle of minus 180, and that gives us two conditions that need to be satisfied that govern the closed loop poles of our system. Those two conditions, we have the magnitude condition and we have the phase angle condition, which says if k is greater than or equal to 0, then the phase of g of z is minus 180 degrees on the root locus. In this particular case, if we're looking at values of k for stability, we can start playing with this magnitude condition. We have k, which is non-negative, times the magnitude of our transfer function g of z. That product needs to equal 1, but our system is pretty straightforward. Or k is now just the magnitude of z. And if we sketched that in a root locus, we have a pole at the origin, and based on our phase angle condition, or the French bread problem, sorry I'm wearing that out, but I think if I say that, you know what I'm referring to. If I say the French bread problem, what's that telling you? How many real axis line segments are now in play in this pole zero pattern? How many real axis line segments do we have? We have 2. How many are on the root locus? 0, 1, or 2? We just have one of those, and that's the leftmost piece, isn't it? And you could look at any point in the negative real line, and it will have an angle based on that single pole of 180, which you subtract the angles of the poles, and that will give you minus 180. For stability, we need that red line to stay inside the unit circle. That red line tells us where all the potential closed loop poles are, and some of those we don't want. We don't want to crank up the gain so much that we go or drive our closed loop pole outside the unit circle. We don't want that to happen. And that then gives us our upper bound on the stability of this system. We can now say, what is the maximum gain for stability? Is it clear now that we want to look at the gain when when z is right on the unit circle, or when z is equal to minus 1? It doesn't make any sense to evaluate k with z equal to 1. In this case, it's going to give you the correct answer, but it's not the right process. Is it clear that the closed loop poles are never going to be at z equal to 1 for this configuration of a proportional controller? There's no way that we will have a closed loop pole anywhere on the positive real line in this configuration of a controlled system. The maximum we can crank up k and still remain stable is to get us right to the stability boundary, which is right on the unit circle, or a value of z equal to minus 1, which is now, and that's why I said it's going to give you the correct answer if you plugged in z equal to 1, because we're taking the absolute value. But now for stability, we can have k varying between 0 and 1. Let's pick a value for k just so that we can compute some other system properties. Suppose k is equal to 1/2. And on an exam, I might give you this block diagram, and I might say, is the system stable with k equal to 1/2? And there's a lot of different ways you could solve that. You could plug in or find the closed loop transfer function and evaluate your closed loop denominator for your closed loop poles and just find the result. You could sketch the root locus, evaluate the maximum gain, and you see, oh, it's 1, and it's between 0 and 1, you're stable, so 1/2 is stable, and that's how you could justify your answer. I would hopefully say, is it stable, and justify your answer. If I didn't say justify your answer, I might have to just accept a yes or a no. A no would be incorrect. You wouldn't want to answer that for this. But is everyone comfortable with claiming that this is a stable value for the gain k? As I said, you could just plug it in here. And now we have our closed loop transfer function, T sub c. What's the DC gain of that now controlled closed loop system? Or how do we find the DC gain? And I've given you part of the answer. It's related somehow to T sub c of z, your closed loop transfer function. This is when you plug in z equal 1. You're not trying to find the gain with z equal 1, the k gain. You're trying to find the system gain. So this is getting maybe a little too confusing, but is it clear the difference between the gain k and the DC gain? Those aren't the same. The DC gain you do find by evaluating this at z equal 1. This now you simply replace all of your z's with 1, which there's only one of those. And now you have a DC gain of 1/3, which means if you put in a value of 2, you're going to get 1/3 of that at the output. That's what the DC, if after the transients have vanished. You put in a 3, you're going to go to 1. Is that clear? Which means that you will have some steady state error. Your steady state error is just the reference input in the steady state minus the steady state output value, y sub ss, and let's just compute this for a unit value or a constant of 1. What's y sub ss? That's just the DC gain times the input, which is 1/3 times 1, or 1/3. And now you put in a value of 1, and where do you go? To 1/3. You now have a steady state error of 2/3, which may not be acceptable. If you go into your boss and you say, I stabilized this delay, this unit delay, I stabilized it with a controller, a gain of 1/2, I'm paying you how much? Is what your boss might say. And she might say, what's the steady state error? And you go, oh, it's 2/3. Is that acceptable? And maybe you'll find out that that's unacceptable. But it might be perfectly fine. You just have to, it depends on your system. Let's suppose that it's not acceptable. Now what do? You say, okay, that's not acceptable. I'll be back with a different what? A different gain? Yeah, you might reduce, but then your transient might be. Where is your closed loop pole in this configuration? What is R? You just have one pole in your closed loop system. What is your closed loop? Where's your closed loop pole? There's your closed loop transfer function. Can you now tell me where your closed loop pole is from that? It's where the denominator vanishes. And where is that? Z equal minus 1/2. That's on the negative real line. Now your output might be banging around, back and forth, back and forth, back and forth. Maybe not the best response. Even your error is not very good, but the transient might be even worse for you because now you're going back and forth with your output response since you have a negative pole. There might be a couple of reasons why that particular controller is not acceptable. What if we now change the controller structure? And the next logical step up from P is PI. So let's now look at a PI control. Since this is by design, will enhance our steady state accuracy. What does that mean? If I give you a constant, what's going to be generated at the output? If you have a PI controller and you can stabilize your system with that PI controller, and that's the if you have to guarantee. If you can't stabilize your system, then you need to try a different controller. But if you can stabilize your system with that PI controller, then if I put in a 2, what are you going to see at the output? 2. You're going to have 0 error due to a constant. I put in a 5, you're going to get a 5 out. I put in a 10, you're going to get a 10 out because of that PI structure. Let's now apply this PI controller. If we sketch the block diagram, there is our PI controller structure generically, an adjustable 0 and an adjustable gain. We're not changing our plant, that's still the 1 over Z, which is just a delay. And we are going to retain the unity negative output feedback. Where now, if we wanted the closed loop transfer function, in terms of formula, that's the same as what we've always had. That's our cheer, CG over 1 plus CG. It's just now our C is a little bit more involved than what it was with a proportional controller. Our closed loop dynamics are governed by the denominator of that closed loop transfer function. And now we can say, oh, we have a 1 plus a k z minus alpha over z times z minus 1 equals 0. And now, if you wanted to, you could say, oh, I need to maybe understand what the root locus of G bar looks like. If I know what G bar looks like, its root locus, now I know all the potential closed loop poles for that PI controller. what is fixed and what is not fixed so far in that PI controlled system? Are your open loop poles? Can you mess with those? No, they're fixed. One is at the origin and one is at z equal to 1. What you do have the ability to adjust is that real 0, the alpha value. Any suggestions on where we might locate that alpha? And based on what you know for the root locus, would that help you decide what you might do for that choice of alpha? Here's the root locus. We have a pole here and a pole there. Does that help us decide where we want to put the 0? There's a lot of different choices. Could we cancel the pole, any of the poles with a 0? I'm just seeing if it looks any different if I come and sit in the bleachers. Tired. I'm not getting up now. Can we, I think I've canceled a pole by sitting down. Sorry. I better get up or I won't get up again. Can we cancel any of those poles? Theoretically. And live to tell it. On the exam, can you cancel any of these poles? How many? Thumbs up is yes, we can cancel one of the poles, and thumbs down, no, we can't cancel any of the poles. 1, 2, 3. I see some mixed results. Why would we not want to cancel any of those poles? Is there something wrong with canceling the pole at 1? We can't, right? It's on the boundary, so we don't want to cancel that pole. So that's partially okay to say we can't cancel the poles, but can we cancel that pole at the origin? Yeah, it's inside the unit circle. We can cancel that one. That one's okay if we wanted to. And then it gives us a pretty benign root locus, doesn't it? What's our root locus do if I cancel that pole at the origin? It's the entire left hand. That's what we had before, except now we're starting at z equal 1 and going to minus infinity. That's too easy, so let's do something else. But you could do that. Is it clear that you can cancel that pole? And that would be a very straightforward, simple controller and a controller to design. You could put the 0, let me make it a different color. So this one was okay. That's okay. Is this okay? If I put that Z, maybe I should just do a lot of different, because I shouldn't be just erasing these. So let's say this. That's okay. The root locus would be this. Is there a bound on the upper, is there an upper limit on the gain k? Yeah, you don't want to push it outside the unit circle. What about a different root locus? What if we did what I just said before? We have our two poles, and now we put a 0 there. How many real line segments now exist? And the number fits on your hand, so I want you to show me fingers at the count of 3. 1, 2, 3. I shouldn't be seeing any thumbs, should I? There's 4 real line segments. How many of those are on the root locus? Again, show me fingers. 1, 2, 3. Now I should see 2 digits, right? There's 2 root locus, or 2 sections of the real line that are on the root locus. Those are here and here. What's the pole 0 excess? 1. That's not a hard question, is it? So how many branches of the root locus are going off to infinity? 1. And where is that infinity located? At minus infinity. How many root locus branches are there? Does that have anything to do with the number of real line segments on the root locus? Not really. There's 2 branches on each of these line segments. Is that clear? So now what you would want to do is, this guy is going right, this one's going left. They're going to meet, not necessarily right in the middle, but once they break away at the relative maximum, that establishes a radius, and that radius is this circle. This is why you might even want to bring a compass to the exam. You could put the pin of your compass right at the 0, and that's the center of your circle, and you now have a circle. Oh, that's supposed to be a circle, and you have the other piece of that circle, and the re-entry, you wouldn't even have to compute it. It's r distances away from the left of that center of the circle. Meaning, one branch is here, and then let's say it goes up, and then it goes down, and it comes in and meets this other branch, and one goes right and one goes left. So you have 2 branches of the root locus, both between the poles and between the 0 and minus infinity. Is this one going to be more challenging to try to control? And where is that blue circle going to be located? The limit, well, no, not the limit. One option is if it slid all the way to the right and just canceled that pole, what happens to this root locus? That circle goes away, and now you have just the one line segment of the root locus. So the extreme case there. But this is okay. Is there, depending on where you put that 0, may influence, it will definitely influence the radius, and that radius may go outside the unit circle. Yes? So now the question was, do we have to solve for the breakaway? It depends if you're on this question and there's 1 minute left on the exam. I wouldn't solve for the breakaway. I'd say it lies between those two poles somewhere. It's not equally distant necessarily. You should calculate it if you have enough time. But once you've calculated where that is, this is now between 0 and 1. You could calculate that, and let's say it's 0.6 is where it breaks away. And now well, that depends on where that 0 was located, and I didn't tell you where that was. So you'd have to first pick the 0. If it was at -1/2, now you have a radius of 1.1. And that radius now, and where's your reentry? 1.1 to the left of -0.5. So it's at -1.6. It's a perfect circle with this combination of poles and 0. 2 poles on the right of 1, 0. But once you found that breakaway, now you have this perfect circle. And the reason is that every point on that perfect circle has an angle of what? -180. And how do you determine where you place your closed loop poles? Then you figure out what the gain is to get you to that particular point. And maybe you want to locate your closed loop poles right there, assuming that triangle is still inside the unit circle. The unit circle, I'm not going to be able to draw it. My red circle's not very circular either, is it? But here is a unit circle. Is that clear? And if that's true, then there's an upper bound on the gain K before you start to get outside the unit circle, and you never come back in to the unit circle based on this diagram. And you never would with both poles anyway. And you have to have all of your poles simultaneously. If you had 10 poles, if they're all 10 not inside the unit circle at one time, you don't have a stable system. All it takes is one pole outside the unit circle, and you do not have a stable system. I actually wanted to, so is everybody okay that this pattern is acceptable within constraints, just like the other one within constraints? This one is okay. I actually, in my notes, had just one choice for alpha. And that alpha, I was going to let alpha be 1/2. Is that okay? So now I come back up here. Oh, I just feel like playing, I guess. Not only sitting down, but I'm now playing. If I take this, and if I didn't want to do that. Should have just typed it in. Let alpha equal 1/2. Now what's the root locus look like? How many segments, real line segments, are now identified? 4. How many are on the root locus? How many branches of the root locus are there? Are there 2 branches on that real line segment? No. Now there's just one branch, and there's just one branch here going off to -infinity. Can you now use the magnitude condition to tell me the maximum value of K for stability? Now let's say, what's the range of K for stability? Our magnitude condition says we have K times Z minus 1/2 Z minus 1 equal to 1. And we can solve that for K so that now we have Z minus 1 over Z minus 1/2. When K is equal to 0, where are we at with our poles? Where are our open loop poles? They're at 1 and 0. So we may have to crank up the gain just a little to get us inside the unit circle, but basically the lower bound on our K is 0. Is that clear? What's our upper bound? Now we can use this expression to find the upper bound for K. And what's going to determine the upper bound on K in this picture? This is now our Z-plane. I'm hoping you're okay with this pattern for the pole 0 diagram, the choice of alpha. That's in a PI controller. Now you're looking at you can crank up the gain only so far as pushing that leftmost pole through the unit circle at -1. And you can determine that K value by evaluating this expression for K at Z equal to -1. And you don't even need much of a calculator to do that, do you? Now you know the range of stability for, or I'm sorry, the range on K for stability. What's the steady state error? Drawing so many root loci, you forgot what we were even using for a controller maybe. On an exam, you might simply make the comment that, oh, this is at least a type 1 system, meaning we have at least one pole at Z equal 1. Consequently, we're going to have 0 error due to constant inputs. If you had extra time, you could verify it, which is what I want to do now, just to convince you that indeed that is true when you have a pole in the open loop at Z equal to 1. The error is now the difference between R and Y. For this system, Y is now T sub C of Z times R of Z. We can now factor out the R, and we have 1 minus K Z minus 1/2 over Z times Z minus 1 plus k z minus 1/2. I hadn't yet picked a k, had I? I just had located we know what k needs to be stable. We need to pick k between 0 and 4/3. But now let's just leave it variable and see if it matters in this steady state error calculation. If we want to know what the time domain steady state error is, that's little e at infinity, which is the limit as n goes to infinity of e of n. But in the z domain, that's just the limit as z goes to 1 of z minus 1 times e of z. Just like in the analog setting, or in the Laplace case, it was s, e of s, that you were looking at the limit as s goes to 0 for the final value theorem. Suppose we let our reference input not just be unit step, but let's just say it's a constant a. That's now what r is when it's a constant input, with r of z now the transform of a constant a. We can now calculate the limiting value of our error. That's the limit as z goes to 1 of z minus 1 times this mess, but let's put it all over a common denominator so that I now have that z times z minus 1 plus k z minus 1/2 minus capital K z minus 1/2. That was the denominator, and that will appear here. And then I have the other starting piece, and all of that is times r of z. This z minus 1 can cancel that z minus 1. That's pretty clean. That now disappears. And we're looking at the value of that expression as little z goes to 1. And the only thing left upstairs is z times z minus 1. As z goes to 1, we have 1 times 1 minus 1, that's 0. Is the downstairs well behaved? The left piece gives us 0 plus k, which is between 0 and 4/3, and 1/2. That's okay. So we have a finite denominator, which is good. It's not going crazy. We now have 0. And that's what we said we were going to get. That pole at the origin, pole at z equal 1 for a discrete time, that was our integrator. That was giving rise to this z minus 1 factor that popped up into the numerator. So this 0, which is what we were anticipating, resulted because the numerator forced to equal 0. Because of the open loop pole at z equal to 1. Questions on that? Yes. So now is this an improvement on the delay? And now the question could, or the answer could be it depends, but maybe the delay is not very well behaved. Maybe there's some uncertainty in the gain. Maybe it's like not 1 over z, but it's now 0.9 over z. Maybe this is a messy delay or kind of a weird. So feedback and controlling helps make the system more robust. If this was a easy system to always produce, this easy delay, maybe you're okay with just waiting and getting the output that you just put in one step into the future, especially if the delay is tolerable for whatever you're sampling at. The delay is your sample period. But it really just depends. This was a trivial example just to help us illustrate this concept of the difference or the comparison of a P with a PI controller. And that was the main focus of this. But in general, your G, it may be having all sorts of variation, and so the controlled with feedback now makes your closed loop system more robust. So you could think of 1 over Z getting spit out of some manufacturing process, and you're wanting to package it so that it looks more the same with all of these widgets coming out the door because you're hanging this controller around it. As a commercial, instead of having that 1 over Z, maybe you look at G of Z as 1 over Z minus 2. I now talk about that in the next lecture, which I said is already posted on D2L. I'll squeeze this one in between the previous two and that one, but you should watch that one before exam number 3. So we'll stop with this lecture. Thank you for being patient, and we'll pick up with our review, and good luck on your exam.